enough messing around. Let's get into some genetics.
Another episode of the Science Dudes. I think that's what we called ourselves last time.
Wasn't that?
Genetics dudes, maybe. Dudes wearing jeans. We'll work on the name.
Still working on it. Anyways, we'll get right into it so we don't waste your time, Sister Mills. Anyways, how are you doing? I hope you're well and your family is well. Anyways, we're going to get started. Question 1 has to do with blood types, also with, I think the proteins that are on the blood, and so like the Remus blood groups and the MN blood group traits. So they explain how the heredity of each of those works. So A and B blood types, or the A and B and the I traits are codominant, I believe. And then R for the Remus group is kind of normal. So there's a big R for dominant, and that makes it positive. So that can be heterozygous or the homozygous dominant, or the heterozygous, or all three, or both those two genotypes are the Rh positive phenotype, and the little r recessive is the negative Rh. And then M and N are the same as blood type, they're codominant. So it has to be homozygous for M to be M, has to be homozygous N to be N, and M and N together make M and N phenotype. So we'll get into the questions. First one is a child born with a blood type O, Rh negative, and M is born to a woman who has blood types O, Rh, and Mn, and a man who has blood types A, Rh plus, and M. Determine a positive genotype for each parent and for the child. So basically, you just have to go through for the first, actually for all of these, just went through, and this is father, mother, and in order to get an offspring that is II or a O blood type, then both parents have to have the I genotype or I allele in them, so that it will be passed down through both of them, or else it will be dominated by the A or the B. So you had to check the father mother for the blood type, for the father mother for the R plus and negative, and then father mother for the M and N. So we got the father, possible genotype for the father would be I, big R, little r, and MN, two M's, and then the mother would be II, little r, M and N, which would make the child little r, or II, little r, MM. So the next one, it says, what portion of children born to a man with a genotype AB, R, little r, or big R, little r, MN, and a woman who is AI, R, or big R, little r, NN, will have the blood type B, Rh negative, and MN. So for that one, do the same thing. This is where I calculated the genotype, or the crosses between the father and the mother. In the blood type, the Remus and also the MN trait for here, and got the four. It's kind of like the forked line method, but it's a kind of a hybrid of the Punnett square forked line method. So that's the percent that would be have the outcome as a B blood type, Rh negative, and Mn, and it would be 1/3 of the offspring would be blood type B. Can I just say negative? B negative, Mn. So then for C, it asks for another proportion, and it gives you the genotype for the father and for the mother, and then asks for a specific genotype for the proportion that would come out with a certain genotype. So for that, just did the same thing. This time I FOILed it out, so it's more like the fork line method, and I saw that 1/4 of their offspring will be B blood type, 3/4 of the offspring will be the positive blood type, and 1/4 will be the M blood type. So that means 3/64 of the children or the offspring will be B plus M. And then for the last question, it's a little more tricky, but basically the same thing. A man with a blood type B plus N says he could not be the father of a child with a blood type O negative and MN. The mother child has a blood type A or A positive and MN. Is the man correct? Explain. We say that he is incorrect. He could be correct, but he's incorrect in saying that based solely on the phenotypes that he is not the father, because if both the mother and the father are, you should say it there, have at least because the offspring has to be O, so the father's B and the mother's A. If they're heterozygous or have like the recessive I gene or allele, then they can have a child with an O. And if they're heterozygous for the remus with a recessive little r, then they could have a negative child or offspring, and then M and N, just that's what's going to happen. It's pretty clear that will happen if the mother is, just based on the NN and the MN. So based on those genotypes, there's a 1 in 32nd chance of those parents having a O negative MN. So father was wrong in that case. Sorry, it took 7 minutes to answer the first question.
So question number 2 is the one that's dealing with it's dealing with the chickens and their comb shape. And so pretty much all we're going to really be doing on this one is we're just going to have to figure out which genotypes are going to give us the phenotypic ratio that we're looking for. So in part A, we're looking for a 1:1 to 1:1. And so the way that I did that is I just did the FOIL method. I just thought about what genotypes would get me the ratio that I needed. And so what I came out with is that one of the parents would have to be heterozygous for both traits, and then one of the parents would have to be homozygous recessive for the other traits, or for both traits, I mean. So then for B, we're looking for a 3:1 ratio for the rows and the single comb. And I did the same exact thing, and something that I did that you can do to check your work is you just account for everything. So I made a little key here. I don't know if you can really see that. I made a little key here just to double check myself, and then I FOILed everything out just to make sure that I would come out with enough of everything to come up with 1 walnut, 1 rose, 1 pea, 1 single, and same with B. And I did that with C and D as well. But for C, we're looking for a 1:1 ratio for a rose and a single, and the genotypes that I came up with for the parents would be big R, little r, and homozygous recessive for the P gene, and then the other one would be homozygous recessive for both traits. And for D, we're looking to get 3 walnut to 1 rose. So we'd have a homozygous dominant trait for the R, and then heterozygous for the P, and that's for both parents, and that will give us the ratio that we are looking for on both of those. But again, like I said, it's really important that you go back and just account for everything and make sure that you're sticking everything in the right place, so that way you're coming out with the right ratios. And I believe that about covers everything. Anything that I missed that you can think of?
I can think of. I did it. Oh, explain. I just did it a little bit different. So I just drew out like the Punnett squares, and across the top is the one. Just because they're all in fourths, the ratios that we were talking about. I just kind of, the top ones are the ones that I was looking at, kind of separating the two alleles. So each one for each separate allele, or each separate chromatid is, or sister chromatid, comes down, and usually I would just have, since the second R, the second P didn't matter, I'd usually just have them all a single cone, so that the lower ones would, or the recessive P's would go across, and then I make sure that I have like the dominant ones across the top. So it was a little bit different, but we kind of tag team made sure we had them all right. So now we're on to 3. This is a Palomino horse, is a golden yellow coat, chestnut horse is a brown coat, and the Carmelo horse is a coat that is almost white. A series of crosses have been between the 3 types of horses produces the following offspring. So they give you a bunch of examples, or you gave us a bunch of examples. I guess we're talking to Sister Mills. Pretty much if you mix brown with white, you get a lighter brown, which is similar to Palomino. So this is similar. This is an example of partial dominance, or incomplete dominance.
Partial or incomplete?
Partial or incomplete. Synonymous words. Synonymous. Good thing this is genetics and not English. So like, it explained that. So it's just like similar to the problems we were given where a white, what were the purple flowers?
So it was the white and the red.
The white and the red.
Pink is
it came out as pink was the intermediate. So it's similar to that. And if you did, even though they're not like exact fourths divided, the ratios are the same if you did it on a Punnett square. So for example, so like the chestnut brown would be homozygous, and we're not really say dominant or recessive, but we did put it like as a capital. Chestnut was a capital C, Carmelo was a lowercase c, and those are both homozygous. The Palomino would be heterozygous, and heterozygous comes out with a different color. So that's why only when because like when you mix a chestnut and a Carmelo, they're both homozygous, so which means that you cross them both, they're going 100% of their offspring are going to be Palominos, which is the heterozygous. So 2 homozygous mixed is always going to make that are of 2 different, or recessive or dominant, or 2 different. In this case, we'll make 100%. 100% heterozygous or mixed. And then when you mix 2 heterozygous, the Palomino mixed with the Palomino is when you can see all of them come out. And that's like, I guess I did that on this other page. It's kind of just a crappy, we were just kind of talking about it and I drew it out.
Oh no.
No, that's the other one. But I drew it out here. They all look like C's, so it looks bad, but this top one is going to be chestnut because it's the CC. And then these 2 are going to be the heterozygous, and then this one's going to be homozygous, is also for the white one, the Carmelo. So that's where you get like 5 of them are chestnut, 5 of them are, or 6 of them are Carmelo, and then twice that amount is 13 Palominos. So it's roughly there, although it would be, if it was exactly divisible by 4, it'd be different. But anyways, that's our answer. So possible genotypes: big C, little c, and then big C mixed with little c for Palomino.
Right.
There you
Palomino power. Anyways, we'll kind of just blow through number 4. It's mostly just you get them from the notes and make sure you do the reading, and you'll pretty much come up with all of them. So for A, we got glycosyl transferase and galactose as the enzyme in the sugar that we talked about in that question. B, we got overdominance and heterozygote advantage. C, we got incomplete penetrance. D was incomplete dominance. E was PKU, or I think it's pronounced phenylketonuria or something like that. I don't know.
Sounds right.
And then F is lethal allele inheritance. And then G and H are talking about the maternal. Okay, sorry about that. So G and H are talking about the maternal effect or maternal inheritance because we're talking about the snails and the shells. So what we got for G is we got 3-2 dextral and sinistral. And all we really did is we just took the percentages of the females' phenotypes and then we just transferred that out to we transferred that over to
sorry, is it my turn yet?
their genotype.
Sorry.
And then for H, we did the same thing except for it was kind of flipped because it's talking about the plants. You just take the percentage and then you get your ratio from that. We got 2-3 in a green to white.
Good. Okay. We're going to wrap up with the last question. This one is the one about the guinea pigs. The alleles show complete dominance in the order black is dominant over sepia, cream, and white. Sepia is over cream and white, and cream is only over white, and white is the lone recessive loser. So basically, just chose the two different alleles, made sure they were in each of the parents. Kind of had to fiddle around to make sure they were in the right place, but we FOILed them out. So B, which is dominant over S, is going to make 1, 2 black, and then the S will come over here and go 1, 2. S is, so that makes a 50-50, but the blacks are heterozygous, but the black is dominant over sepia. So, but sepia can be heterozygous or homozygous with itself and shine through. So, or not shine through, but it would be there because it's second half. So, the same thing with the S or with B, sepia and cream, except for they're both homozygous or heterozygous for SC mixed with the SC, and that would give us 75% sepia and 25% cream. The S's would dominate over them in the first 3 squares, and opponent square in the far down corner are going to get both those two C's, recessive C's together. B and C is was a little more tricky because that one we had to have 3 different alleles in there. So we did BW mixed with the BS guinea pig, which I used the wrong one, but I drew it out. Just quicker, but it's supposed to be a W, so we changed some of the W's. But you can see the B is going to be dominant over the W. But both of them are going to have a white in them, or else the white will never shine through because it's the recessive to everything. So there's got to be a white in both, and it's going to be down in the far right corner as the 1/4 or 25% is white. The other ones are 50% black, and then this cream will come over to the corner and mix and be dominant over the W, over the white. So that's what we got there. And then the last one, 75 and 25. Black is dominant over white, but white needs to be in both. So it's W or black W, black white mixed with a black white heterozygous pair. Black will go through the first 20 or 75%, and then those 2 white recessive will go into the far right corner of the opponent square.
Basically a 3-to-1 ratio.
3-to-1 ratio.
That's what we like to see.
Yeah. Anyways, it's been fun having you watch us. I hope it wasn't boring. Sorry that it was 20 minutes long, but you can watch it in double speed hopefully. or
something.
just skip to the questions that you're gonna grade?